Welcome everyone, I'm Simone Parisotto. I'm going to chair this webinar session. Before starting, I want to remind this is a recorded event and the video will be uploaded on our YouTube channel. So by staying with us, you agree with this policy. And I invite all the attendees to mute their microphone and turn off their camera for now. This event is part of the AI&ARTS webinar series. AI&ARTS is the interest group at the Alan Turing Institute in the UK promoting cross-discipline interactions between the arts and STEM disciplines, particularly related to the usage of artificial intelligence in the art sectors. And you can get a glimpse of our several activities at our webpage. I will put shortly a link in the chat. And we are very excited today to have as speakers Dr. John Delaney and Dr. Tania Kleynhans. And first of all, I want to thank both John and Tania for their efforts in joining us, as they are in a very inconvenient time zone. And John is a senior imaging scientist at the National Gallery of Art in Washington. He's an expert in remote sensing and processing methods for the study of paintings and works on papers. And Tania is a research associate at the Rochester Institute of Technology. And among several research interests, today I would like to introduce her as expert in pigment identification in paintings with machine learning and artificial intelligence. And that's why today the topic is very much related to this area of research. And the title would be an alternative approach to mapping pigments in paintings with hyperspectral reflectance image cubes using artificial intelligence. So John and Tania, the stage is yours.
Thank you. John, you're muted.
Thank you. Thank you very much. I'll start the slide presentation. Okay, well, it is a real privilege and it always does that. Real privilege and honor to speak to this group. We hope to share with you two parts. One is an overview of the research that we're doing at the National Gallery, the different imaging modalities that we're collecting data in, the various kind of data sets we have, the type of image information and material information we're mining from these data sets. A lot of this is done quasi-manually, and so we're very interested in looking for colleagues that would be interested in taking on some of these data sets and doing new things. Tania will speak about a project that she was involved in and drove pretty hard to try to solve one of our biggest problems, which is trying to automatically identify and map pigments from these data sets. Okay. So in terms of the talk outline today, we're going to start off with reviewing the imaging modalities that we make use of. One is based on reflectance imaging spectroscopy, and the other is X-ray fluorescence imaging spectroscopy. Some of you may know of that as by its acronym MACRO or MAXRF. And then I'm going to discuss applications to painting analysis. And then in the last part of the talk, we're going to focus on artist material identification and mapping. I'll start off talking about the traditional methods using convex geometry, and then Tania will go into some depth about her research on looking at artificial intelligence as a solution to that manual effort. Now, just a quick review of reflectance imaging spectroscopy. First, I'm showing you the electromagnetic spectrum, X-rays, UV, the visible where we all see and live, and then the near IR and SWIR, which is the part of the infrared which is not, it's not thermal in the sense of sensing heat, but there is energy there that can be exploited. And what we call the mid IR, which is the vast portion of the infrared, which is thermal, in the sense that there's more energy emitted by the object than reflected from natural sunlight. And that's the region that's very rich with all of these vibrational lines. We are essentially working in the range of the visible and the near infrared, or called SWIR, depending on your discipline. And we're looking at overtone and combination bands in the near iron sphere from functional groups like hydroxyls and carbonates. And the visible, we're obviously looking at electronic transitions that provide information about color. I've given you on the right here a physicist's view of a paint layer, where essentially we have these absorbing small pigment particles within a binder of an index close to or matching sometimes that of the actual pigments. And the light interaction we're interested in is the light that makes its way into the paint layer, is scattered, preferentially absorbed, and then is emitted out. As we shift to longer wavelengths and we make advantage of the fact that the scattering is minimized, sort of a me-scattering solution, then these light rays in the deep red can penetrate all the way down to the white ground layer, reflect off the white ground. So the preparatory sketch, a layer that's put down by an artist on which he or she may actually do a preparatory drawing, which would absorb more of the infrared light. And so we'll get a contrast difference in the emergence. Now, the definition of reflectance is the ratio of the irradiance coming out of the paint layer, the backscattered light, to that of the input. When we actually collect our data sets, when we do reflectance imaging spectroscopy, we're essentially measuring the reflectance spectra as a function of wavelength at all spatial points across an art object. And here I show you a hyperspectral image cube of a work by Pacino, an illuminated manuscript. And I'm showing you that the two spatial dimensions and then the wavelength or energy direction. And as you can see, we end up with a tremendous amount of data. We've got 745 spectral bands. So essentially, you can imagine we have 174 different images of this painting in very narrow spectral bands, all aligned. Now, of course, these data sets can be mined, and we can pull from any spatial point the reflectance spectra, which is the amount of light that's reflected back at any given wavelength versus wavelength. And it's a powerful technique. It's essentially picking up from remote sensing of the Earth, looking and identifying minerals. It's been extended extensively to the study of Mars. And we're able to look at the electronic transitions and then these hydroxyl features, these functional groups, carbonate groups. And from this, we can separate, for example, two very similarly colored blue pigments. They're both minerals, one being ultramarine or lapis lazuli, and the other being azurite. And you can see the difference really is in the near IR, where there's electronic absorbance difference, and the presence of these functional groups. Now, of course, we can take a reference spectra or take a spectra from the cube and ask which pixels have the same spectra to make maps. And that's really what we're trying to do, is get the distribution of these pigments within the works of art. And here I'm showing you in green the distribution of azurite, and the distribution of ultramarine here is in blue. And we see that ultramarine, which is a very expensive pigment, is only on Christ, whereas the majority of the blue is surrounding the apostles, makes up the floor and the border. Now, this provides molecular information, which makes it a more straightforward way to identify pigments or artist materials. The other technique is X-ray fluorescence, where, of course, we're working down in the X-ray region to excite inner core electrons and look at the fluorescence. And in a very analogous way, it's a point scanning system, but we end up with spectral information versus spatial position. So another 3D cube, which we can mine and get to the emission spectra at any point. Now, right off the bat, you can see from a signal processing point of view, there's a certain advantage to XRF. Instead of those broad reflectance spectra I showed you, now we have narrow emission peaks. And more importantly, scientists know exactly where a given element will give its emission. So we can be more deterministic in terms of the identification. Now, since we have this information spatially across the image, it doesn't take very much to integrate a peak and then make a map distribution. And here you're seeing the distribution of copper from the K alpha line. And it won't surprise most of you to see that its distribution matches that of the actual azurite, which is copper containing. And then, of course, where I said there was ultramarine on Christ, of course, you get no signal. So those are the two major imaging modalities we're using, and other people are using at many other institutions. Just for the aficionados, the instrumentations that we use here, we've built our own macro XRF scanner some years ago because we have an easel that moves the artwork. So we can upgrade our system as the components improve over time. And we're also building our own hyperspectral camera system for similar reasons. The only thing I would admonish upon you is the time that it takes to do these collections. For the point scanner or single pixel scanner in XRF, to scan 1 square meter at a 1 millimeter sampling takes 12 hours. If you want to get an integration time that gives you good signal to noise for the spectrum. Similarly, because of the Felgate advantage, well, in this case, not Felgate, but the multiplex advantage of our hyperspectral reflectance cameras, where we have 1,000 pixels along the silhouette, we're collecting 1,000 pixels at once. So it's just a push broom or whisk across the painting, and we can do that same collection, area collection, resolution, but in only 5 minutes. So it's no surprise we spend a lot of time first collecting data sets with the hyperspectral camera, getting reflectance information, and then going back and doing the elemental information, XRF scanning as needed. Now, to do all this, there's two things you can do. You can move the cameras or the XRF scanner, or you can move the painting. In our case, we're very lucky to purchase from a UK supplier, originally StatScan, but now it's LG Motion, a custom easel that is safe and secure enough to actually move paintings at the speeds that we need and with a precision, spatial precision, to be able to assemble large mosaics. And this is a setup here scanning a Fragonard painting where you're seeing our XRF system running with a red light saying there are X-rays on. Okay, well, what do we do with this information? What do we do in terms of trying to address questions that conservators, art historians have about works in our collection and also works at other museums and institutions, since most of our equipment is portable? Well, a lot of the objects in collections at museums, the provenance is well known. So we're really not going to contribute much in terms of, is this by so-and-so versus another person, or is this a fake? But what we usually get asked is what changes were made, and maybe by what artists when multiple artists had their hands on the painting based on the historical record. And an example of that is the Feast of the Gods, which was started by Delaney and then later finished by Titian. This is a painting that was in the Qualitative Evaluation and within the family. And it was one of a series of paintings in this alabaster study room or office that the Duke had. And he started off with the painting being done by Delaney late in his career, and Delaney's student Titian eventually came back and updated it to be more aligned, I guess, with the styles of the day. And there's always been a question as to what changes were made by who. And essentially, you can see it's a collection of the gods. You can see Bacchus here. Obviously, they've had way too much wine, or at least some of them have. But what's really important is this background. You see these beautiful trees, and then you have this rather large hillside, and on top of it, you have these ruins here, which is obviously where the gods live. And you see this animal, satyr on the hillside. Well, early studies just using X-rays had shown that there were a whole stand of trees originally behind, and that there was another version of the hill that was painted over. So essentially, we have Titian's final changes today as we look at the painting, and we know early on there was a stand of trees in the work that Delaney had finished. So the question we got from the curator is, these are nice schematics, but can we do something more precise to give a more direct visual interpretation of how Delaney had left the painting? This is the painting in our studio or laboratory with various instrumentation, with the reflectance spectroscopy here. And here's the elemental mapping. And you get a scale of the size of this painting relative to our equipment. So it was no small undertaking. The painting was made available for us for about 2 weeks to do this work. So what do you get out of this sort of data set? You end up with a tremendous number of spectral bands in both modalities, and it requires a lot of time to sort of sort through them and kind of pick up an understanding of what's going on. But here I show you a simple false color. So we've taken 3 spectral bands from the infrared reflectance image, and we've put them in the display channels of a computer monitor here, in this case, in green, red, and blue, to maximize the contrast between objects that we're seeing. And the objects that we're interested in seeing here are these trees. You can see the stand of trees, and those are Delaney's original trees. You also see a little funny thing. You also see this little tree that's on the background here, whose scale is completely wrong for Delaney's trees, and it doesn't exist in the final painting. So we know that this is by an intermediate artist, or artist who worked on the intermediate painting, and that would be, it's assigned to Dasso Dasso, as you'll see. But we don't see a lot of changes going on directly with the actual gods, and that was one of the big questions. Now we took this data set along with the new X-ray, as well as transmitted infrared, registered all of that with some of our computer programs that we've developed with George Washington University, and made a series of layered images which we highlighted the information, the new information, and then turned that over to a art conservator who was very talented with Photoshop to essentially put together a more serious simulation based on these technical images of what Delaney's painting might have looked like. And this is the image we end up with now, which is a lot closer to reality, to what Delaney had, than the sketches that you saw earlier. Please excuse my dog, it's early in the morning here. And as you can see, the stand of trees in the background significantly changes the view of the painting and the interpretation. And for the art historian, this really made a big impression on him in terms of perhaps why the scene was changed. I'll leave you a moment to look at the differences. Interestingly enough, there was a big discussion whether this is evening or morning, and that's an interesting question, as the art historian raised, David Allen Brown, which was, how can you tell the difference in a painting if you're given no other information? There's some other things that came out. We were able to pull out a little better the stand of buildings. There's actually a castle in the sky here. In the final painting, you can see there is a ghost image of a building up here. So in the intermediate hillside, there were much more elaborate ruins. You can see a circular annulus here in this building. There's an entranceway. These are some of these smaller trees in the earlier version. And then there are other buildings. There's an arch here, another building over here that begins to pop out. And so tools and techniques to make these buildings more visible are of great interest to art historians. Now, just to show you that since that's all painted with lead, one would think that simple elemental imaging could give you a much better view. This is the lead map of the same area, and unfortunately, yeah, you can kind of just make out this building, but lead was used in the form of lead whites so strongly throughout the painting that you don't get any contrast difference. So each modality contributes its own information, and you need to work with the two of them as what everyone's finding. There's another little interesting discovery that popped out at us. This is a portion of the trees in the background above the some of the central characters in the foreground, so we can see them in the background. You can see that they've been very carefully painted around in terms of these changes in the background composition. It's Delaney's trees. You see this swath of paint that's covering it up, but I think right here you begin to imagine you're seeing an animal here, a deer, and you can also see this tree that we mentioned earlier. This sort of makes more sense if there's sort of a pathway here. And this tree is very different in the styling. If we focus in a little closer and I change the contrast locally, these deers are going to pop out. Excuse me. Take it easy, guys. Sorry. And then if we make an outline, you can see the deer more clearly. And if we do elemental imaging, looking at Mercury, for example, for this one particular deer, we can get a very clear image of him. So this is a whole series of animals on the hillside that no one anticipated. They're a larger scale and very much in the style of Dasso Dossi, who was a court painter at the time period for the Duke. So that sort of ends our work that we've been doing on the Feast of the Gods. And now I'll jump very much closer to the present and talk briefly about Picasso and work that we've studied during his Blue Period to try to understand the paintings that are beneath these Blue Period paintings that everyone's so curious about, because this is a period where he is changing his style very quickly. There are descriptions and drawings. Usually anything he's painted is a drawing. And so there's a lot of curiosity to find the paintings and their relationships. So here's the color image of the paintings that exist today, Le Gourmet, which shows a boy eating out of this bowl. And then a standard infrared reflectogram, a standard technique, just a photograph in the near infrared that conservators use to look at all paintings, shows that there is a woman beneath this boy. And the question that was asked was, is this by Picasso? Is this a drawing? Or is this a actually finished painting? And these are the type of questions that we get from the curators and the conservators to try to suss out. Well, by working in the right spectral bands and making use of model studies to find out what's the best wavelengths to work to minimize the paint that's on the surface, we ended up with this image, which is looking a lot better. We've got one more eye, and there's a little more contrast, and the contribution of the boy is less present, and the necklace is becoming clearer. But it doesn't have any volume to it. It still could be a sketch. So we said, okay, it's a good time to do elemental mapping. So here are the elemental maps for lead, because we knew from our point measurements that these little flecks of white here were due to lead white. The X-ray radiograph had shown us there was high density consistent with lead white, but we couldn't actually see anything in the elemental mapping. And that's because the final composition was painted with zinc white, which essentially blocks our ability to see the lead white XRF signals. But we took a page from remote sensing and actually measured the depth of a hydroxyl feature associated with lead white. And if you start to look at this picture in comparison to the simple infrareds taken, you get to see we're seeing much more volume in her flesh and her cheeks. We're seeing a real sense of paint buildup. We're seeing the two eyes. We can see that she clearly has a necklace, a cross, indicative of someone which is going to or coming from church. And this opened up the possibility to try to really look into whether this is by Picasso. From the elemental imaging, we did find chrome, and the chrome could be thought of as being associated with chrome yellow, given the fact that this is a crucifix. And then what was kind of interesting is we found there were a series of paintings called Women in a White Mantilla that was done by Picasso. This one particular one is in a private collection. It was dated 1905, but Picasso himself actually changed the date back to 1901 when he saw this written up. So now we have a painting in 1901 that becomes very similar in its character and nature to what we're seeing in our composition. So I have done a very crude simulation with color here, using some color information from the Woman in the White Mantilla. So this gives you a perspective of where we start, the data we get, and how it can round out to answer a question. Well, the real heart of the talk today is focusing about trying to do pigment mapping and identification. And the algorithms that we're currently making use of are based on remote sensing techniques that have been around for, I don't know, at least 20 years. The tools we're using are pretty traditional. They're based on a ENVI proprietary set of algorithms that were developed at the University of Colorado in Boulder. And they kind of fall into a simple category of convex linear unmixing, convex geometry. And the way it goes is the first thing you do is you somehow classify regions that all have the same reflectance spectra. In this case, they could be reflectance spectra, could be the result of mixtures of pigments or pure pigments. And then the second thing we do is once we've classified large regions of the painting as having the same reflectance spectra, or similar reflectance spectra, we try to, which we call end members, we try to identify these end members in terms of what pigments make them up. Sometimes we get lucky and there's a sufficient amount of information in the spectral features in the reflectance spectra. Other times we have to reach for the elemental information from XRF. We have XRF maps, and sometimes we even have to go to other tools like Raman or to take samples. So kind of a two-step process. And what I want to point out to you, which is important, is that in normal remote sensing, when you're imaging, you may have one pixel in your data cube that's composed of two different materials, but they're optically thick. So we may have a patch of grass and maybe some, let's say, some road. And the reflection spectra is the linear sum of the weighted areas. In the case of paintings, what we have is very small pigments that are in intimate contact, where the light is rattled around and scattered. And the reflectance that we measure is not the simple sum of the reflectance of these two different materials, weighted by their concentration, but rather it's a result from the scattering. It's sort of a nonlinear relationship to the concentration in the case of intimate pixels. So this kind of violates the linear convex geometry linear requirements or state or condition. Well, we ignore the nonlinear part, as I said, and we just treat these paints as unique reflectance spectra and worry about identification later. The technique, just really quickly for those who are not familiar with it, you start off with your cube. You may have several million spectra to look at, so you're not going to do this by hand. You need to reduce the dimensionality from 145 down, so we use PCA. And somewhere along the line in the 20 to 30s, you basically get down to a small enough data set, so you've dropped from 700 down to maybe 37. And of course, then we do clustering in this reduced dimensional space. And these clusters relate to unique spectra that we can identify in some cases, but certainly can be used to make maps. And this is a set of end members that represent this particular painting here by Pacino. And so we can use a spectral angle mapper method, which just measures in hyperspectral space within the, in hyperspectral space for the different wavelengths, the angle between a reference spectrum and any spectrum in the cube. And then if the angle is small enough within tolerance, we can assign that to that particular material, and then make these maps, let's say, of azurite. And then in this other case of ultramarine, and in this spectrum, we get contributions from both, a layered ultramarine on azurite, kind of a common technique. And this is what you want to show a curator, conservator, because this they can understand, this they will spend some time thinking over. But this is spatial information. It shows materials are being used in a painting process, so it's ready to be understood by them. Same thing again here. I'm just showing you some red ochres used for the robes, brown ochres, and then the complex mixtures of paints that making up the face, which have green earth. There is some mercury present there as well, which is all encoded in this spectral signature. So we can figure out the composition later, but at least we can say the faces are all painted the same, with the same materials. So in the upshot, what you can do is, for a complete looking at this painting by Mary, by Cosmatura, you can end up with this basis set of different pigments, many of which we can identify directly. The red lake, the ultramarines, some in cobalt blue in painting, azurite, iron oxides. And this is the corresponding map using spectral angle mapper. And the only thing that came out that was a little confusing was this rocky landscape, which we said, we thought maybe this could be an umber given its color. But from some XRF data, we knew that the copper didn't extend down here, so it could not be a copper resonate. Did not, we knew that the copper extended down through this region here, and it couldn't be an iron material, so we ended up with copper resonate. Other things we can do is you make a false color in the infrared. This is a very jumbled image, but what the conservators would be very interested in is getting the preparatory sketch done in a black pigment, or in this case, a umber. And there's some confusion. The purple is in paint. This black is, we're not sure. The brownish color looks like it could be this umber pigment, but we could make use of the reflectance spectra at one point here from these lines, make a map of just that particular spectral shape, and we end up with something that looks much more reasonable and clear as a preparatory sketch. And you can see the fine lines, the handling of a very liquid type underdrawing that build up this figure without the distraction of these partially painted areas. Another thing we can do, which I won't go into detail, we can make use of very small absorbance features, overtones, combination bands of these functional groups in the farther spectral region out towards 2300 nanometers, which can be used to get indications of where protein, carbohydrates, and things like lipid features associated with drying oil or egg yolk. And in the industrial chemistry fields, people have used these features to grade and separate different oils, and have been used to look at different industrial materials as well as pharmaceuticals to look for defects in coatings. And so we've essentially exploited that to make maps of binders. In this case, the use of egg yolk is shown here in red, and the use of a protein binder is shown here in blue. And this kind of follows along nicely with the measurements that were taken by microsampling and analysis done by micro HPLC to identify the binders in this painting. And now I'm going to let Tania continue on and talk about the more interesting things, which is what you can do with artificial intelligence to solve that problem of identifying and mapping pigments. Tania, do you want me to go ahead and keep toggling the slides for you, or would you like to take over and show your own screen?
Thanks, thanks, John. And yeah, if you can keep doing this, my internet is a bit spotty, so let's hope this works. So if you can just turn it over when we're ready, that'd be great.
I'll stay awake.
Okay, thank you very much. So yes, as John already mentioned, the current convex geometry methods is a bit slow, and it requires an expert to do the manual clustering. And with slow, it can be anything from a couple of hours to a couple of days, depending on how much detail there is and how many clusters there is. So again, they're then showing that with very often reflectance, a reflectance spectrum is a mixture of more than one pigment. On the left is explanation if it's a linear sum, which it very seldom is with pigments. On the right, you can see the mixture, the reflectance spectrum would then be a mixture, and that makes it a non-linear problem, which makes this whole problem much harder. So researchers have been exploring the Kuban modeling to get pigments and abundances, and they're using the absorption and scattering coefficients to get at that. But to get the details, there's mock-up samples being made, and it is also a bit challenging to get all the information needed to use the Kuban modeling. So we've decided, since neural networks are really good nonlinear function approximators, why not try that? Next slide, John. So unfortunately, as you know, most neural networks require a significant amount of data to train the model. And this is a challenge since there are not hundreds of studied paintings to use for truth data. On the upside, since neural networks are, as I mentioned, great nonlinear function approximators, they should work well if we can find enough training data. So we decided to constrain the problem by looking at a number of paintings from one artist's school, thus limiting the number of pigments and pigment mixtures used. These paintings also included examples of layered paint and colored substrates. Next, John. We decided to create our own labeled pigment data set by using the hyperspectral data. And the data that we have has 209 spectral bands, which start at about 400 or at 400 nanometers and ending at 950 nanometers. And we use the spectral signature as the feature for each pigment mixture or layered structure. This labeled data set was then used to build and train the neural network. And so just to clarify, truth data is defined as pigments identified from various imaging modalities. So not just hyperspectral data, but also from XRF, sometimes Raman, or fiber optic reflectance spectroscopy. We did look at the potential to create mock-up samples for the data set. However, the large variation in spectral signature, even within a pigment or mixture, is mostly not attainable with samples created in a lab. Next. Here is just one example of an illumination that we used in creating the truth dataset, namely Christ and the Virgin enthroned with 40 saints, painted by the master of the Dominican effigies, and it's from the Lidario of St. Agnes. The initial pigment identification was made with the original ENVI method, and spot XRF and force data was added to identify the more challenging pigments or mixtures. On the left is the true color image of the illumination. The middle is the ENVI class map, and on the right, the spectra of the identified pigments, as John has shown before. Next. For the data set, we use these 4 characterized illuminations that I show here at the bottom. And the spectra was selected, like you can see on the image at the right top, just adding all the spectra together in a database. This process allowed for a range of variations in one spectra to be collected. And an example can be seen on the graph at the bottom right here, where we show the variation in the collected spectra of brown ochre. Next. Okay, so let's go into a little bit more on the technical side and information about the model we built. We looked at the various different model architectures and found that the 1D one-dimensional convolutional neural network performed the best. Each feature of the model consisted of one spectrum, so we didn't use any spatial data to build the model. The input data was then convolved with a 5x1 and then a 3x1 kernel, followed by max pooling and the ReLU activation function. And lastly, the categorical cross-entropy loss function was used. The training data consisted of 25 classes, and with classes we mean pigments or pigment mixtures or layered structure signatures. And as mentioned, where each feature was a reflected spectrum of a pigment. In total, we had just less than 17,000 spectra, and that was divided into a 90-10 train test split. And then the training data was trained on 80% of the training set, with 20% used for validation. Next. And in the end, we decided to use two different metrics to evaluate the model. Firstly, the more common method to use for neural networks, we calculated the performance of the model using 10-fold cross-validation and reported mean per class accuracy. Since the classes in the model did not all have the same amount of training data, mean per class accuracy is then the better way to report the results. And 10-fold cross-validation is a method used often to evaluate machine learning models. And how it works is the data is divided into 10 equal groups, and the model trained on 9 of them and tested on the remaining group. And this is then repeated 10 times with a different group for testing every time. And at the end of the 10 iterations, the results are averaged. The accuracy displayed here is the results averaged across the 10-fold cross-validation with a total mean per class accuracy of 98.7%. I know this is very high, but given the constraints of the data set, this is understandable. So on the right here, we see the confusion matrix to show misclassifications. It has been scaled to make the misclassifications more easy to see. The ochres there in the middle were more difficult for the model to identify correctly, which makes complete sense as the spectra, for example, between orange and brown ochre is very similar. However, to validate the model further, it was tested on 2 paintings that was not part of the original training data. One from the same manuscript, and then the other from a different painter and location. Next. So the model was first applied to the Pentecost illumination, and the output of the model is 25 pigment maps. And here I am displaying only 10 of the 25 maps. Each map displays the probability of a pixel belonging to a specific class or pigment, with values ranging between 0 and 1. White areas on the maps have high probability that those areas belong to a specific pigment. And for the final material map, only pixels with a 0.99 probability or higher were used. Next. The model was not evaluated on a pixel-by-pixel manner, but compared visually to truth maps. And again, truth maps or truth data was supplied by experts armed with hyperspectral cubes, fiber optic reflectance spectroscopy, XRF and Raman spectroscopy data. On the left is a color image of the Pentecost, followed by the truth pigment map, and then next to it, the neural net material map, and on the right, the associated labels. The first column of the labels display the truth allocations, and the next column is the neural net allocations. Most of the pigments were correctly identified. Just note, again, as mentioned, for the truth data, a variety of imaging systems was needed. Thus, it's understandable that the neural network cannot accomplish the same accuracy with only data from one imaging modality. Next. Even with this, most of the pigments incorrectly classified were not part of the training dataset, and thus it's understandable that the model would fail in those cases, as can be seen on those there where the highlighted orange dots are. Next. When we zoom in on one part of the illumination, it's noticeable. What was noticeable is that the model identified 2 different pigments in the border of the illumination, showed here on the left. This was something the conservation scientists had not noted before, and after some additional research found that the border on the left was painted over a blue azurite line, as can be seen in the copper XRF map on the right. The model identified this as ochre, and not as red lead with azurite, which is an uncommon layered structure that was also not part of the original training set. However, even though the model was not correct, it did help focus the attention of the conservation scientists on this feature that was not known before. Next. In addition to evaluating the Pentecost illumination, which was from the same book as we mentioned before, this illumination, St. Peter Enthroned, was from a different painter and not from the Florentine period. And even with this change in parameters, the model performed really well, with misclassification mostly due to pigments not part of the training set. For example, the yellow lake was used and not leads in yellow that was part of the original training set. Next. So in short, if you can constrain the problem, which in general neural networks usually have a very constrained problem, and train the network on a given set of pigments in a specific time and place, it will perform really well. However, if you change the parameters and try to identify pigments that was not part of the training set, the model will fail. So we plan to expand the model by adding more collected spectra from other paintings and thus growing the training data set to make it more generalizable. And lastly, moving forward, we would like to apply the model to other leaves in this Lidaria of syntagmies, which is what the training data set was from. Yeah, so that's the work that we've been doing so far. And here's some acknowledgements that we would like to make. I'm not going to read through all of them. So you're welcome to give us some questions if you have. And thank you for listening.
Yes, thank you very much.